Finally, we have come to the notions of extension and contraction of ideals. Let us start by considering a ring homomorphism F from the ring A into the ring B. If I is an ideal of the domain ring A, then it's not necessary that its image under F is an ideal of the second ring B. You can take this example. Consider the embedding of the ring of integers into the field of rational numbers, which actually just does not do anything. It takes an integer and gives it back as the output. You know that this is also a ring homomorphism, it's an embedding. It embeds the system of integers within the system of rational numbers as a subsystem. Now note that the ring of integers is an ideal of itself. You think of this in place of I. But its image under F, which is itself due to what the function does, is not an ideal of the field of rational numbers. Why? Because Q being a field has only two ideals. One of them is Q itself and the other is the zero ideal, and this is none of them. Okay, so it's not necessary that the image of an ideal of the domain ring under a ring homomorphism be an ideal of the second ring. However, in spite of that, f of I is after all a subset of B, and being a subset of the ring B, it can generate an ideal in B. This ideal, B times f of I. And that ideal is defined to be the extension of the ideal I, and we denote it by writing this I superscript E. Let us see what the elements in this extension are. This is how the elements in this ideal look. Summation yi f of xi. It's a finite sum, that means there are finitely many terms in this sum. So obviously we are considering finitely many. Oh, and by the way, what are these yi and xi? Xi are elements coming from the original ideal I, and yi are ring elements coming from the ring B. So a finite number of such elements are involved in this sum. Now we already know what we mean by the ideal generated by f of I in the ring B. It is the smallest ideal of B which contains f of I within itself as a subset. But here we are claiming that that ideal is actually going to have elements that look like this. Let's verify this first. Although we have used the symbol Bf of I to denote the ideal generated by f of I in the ring B, but let us assume for some time that this instead denotes the collection of all such elements, finite sums of such products, where the yi's are coming from the ring B and the xi's are coming from I. Now we want to prove that the collection of these elements, that is B f of I, is really that ideal generated by f of I. Say we want to show that. So what do we do first? We first notice this thing. We take any element x in I, then you can write f of x as 1 times f of x, where what is this one? This one is the identity element in the ring B. And actually it's understood because you are multiplying 1 with f of x. F of x is an element of B, so obviously this product makes sense only when this one is the identity element of B. Alright. And this belongs to this. Why? Because this product is a sum of that type. In this case, this yi is 1 and xi is x. In this sum there is only one term, but still it's a sum, technically speaking. So that's how the f image of any element in I is in B times f of I, and that is why f of I is a subset of b times f of I. So we see that this subset of b times f of I, the subset of all such sums, whatever it is, it at least has f of I within itself as a subset. Alright, and because of that, it is also a non-empty subset of the ring B, because f of I itself is non-empty. And why is that so? That is because I is non-empty, so its F image automatically would be non-empty. So you have now got a non-empty subset of the ring B which contains f of I. Let us next show that this, that means the collection of such sums, is an ideal of B. So next we are going to consider some finitely many elements. Let us consider these elements in the ring B, y1, y2 up to yn, and along with that another list of elements y1 prime, y2 prime up to ym prime, and an equal number of elements in I, x1, x2 up to xn and x1 prime, x2 prime up to xn prime, so that we can form two elements of Bf of I. One of them is this and the other one is this. This one involves the yi's and xi's, and the second one involves the yj primes and xj primes. So obviously these are elements in Bf of I because of how they have been formed, because of their structure. And then you take their sum. Then the sum is clearly again another such finite sum where the terms look like that. An element of B times the F image of an element of I. So obviously this sum is also in Bf of I. So our set Bf of I is closed under addition. Next we consider the additive inverse of these elements there, which is an arbitrary element in Bf of I. Additive inverse where? Additive inverse in the background ring B. So then you know, using the ring axioms, properties, everything, you can write that inverse like this: minus y1 times f of x1 plus minus y2 times f of x2, like that, all the way up to minus yn times f of xn. But these minus yi's are after all again elements of the ring B. So this is again another such finite sum. So this belongs to B times f of I. So if you take the additive inverse of any element in Bf of I in the ring B, then that actually is lying inside Bf of I itself. So combining this and this, you can now conclude that Bf of I is an additive subgroup of B. And we need to show one more thing so that we can claim that this is an ideal. Next we take an arbitrary element B from the ring B and we multiply that element, this element by B. From left side or right side it does not matter because our rings are commutative. And then again, using all the ring axioms and everything you know about a ring, in place of this product you can write this sum by1 times f of x1 plus by2 times f of x2, like that, all the way up to byn times f of xn. So all these by's are again elements of the ring B. So this is another such finite sum. So it also belongs to Bf of I, and that is why Bf of I is an ideal of B, and already we showed that it contains f of I within itself. Alright, that alone does not of course tell us that it's the smallest ideal containing f of I, or in other words, it's the ideal generated by f of I. For that we need to do a little more. Let K be any ideal of B containing f of I. This is one such ideal, but let K be any ideal of B containing f of I. Now next what we do, we take any finitely many elements in I and an equal number of elements in B, so that we can consider this general element of Bf of I. We straight away say that this belongs to K, but let us see in more detail how. What do we know about K? K is an ideal, but before that we also, along with that, we also know that K contains f of I. So for all these elements xi's from I, f of xi, these elements, f of x1, f of x2 up to f of xn will all belong to K because K contains f of I. Alright. So if you multiply any such f of xi, which now we have shown that it's in K, by yi, then that product yi f of xi will also belong to K because K is an ideal. And if you take the sum of such products, that is also in K because again K is an ideal, so it's an additive subgroup of B. That's how this element belongs to K, but this is a general element of Bf of I, and that is why Bf of I is a subset of K. In other words, Bf of I is contained in every ideal of B which contains f of I. So it is the smallest ideal, besides that it is also itself an ideal which has that property that it contains f of I. So it becomes the smallest ideal of B containing f of I, and which means that it is in fact the ideal of B generated by the subset f of I. So now we have finally done it. So that was the extension of an ideal of A. The next thing we see is the contraction of an ideal of B. Let J be an ideal of B. Then the inverse image of J under F, that is this thing, is itself an ideal of A. This was not the situation with direct images of ideals of A, which themselves are not ideals, but we can use them to generate ideals. Here, however, inverse image itself is an ideal, and this fact we have already seen in the correspondence theorem for rings. And this inverse image itself we are calling the contraction of the ideal J, and we denote it by J superscript C. C stands for contraction, just like E stands for extension. Now before I say anything more on this, you note one thing carefully. These notions, actually these notions are there, but along with them we have notations also. No, I, E, J, C. These notations do not show the background homomorphism F explicitly. There is no F in this notation. But these things are fundamentally depending on F. If you change the homomorphism, these things will also change. So don't forget this dependence. Alright. Now besides being somewhat simpler than extensions, contractions are also nice in another way, which is, I forgot to write that line. That line is this: if the ideal J is a prime ideal of B, then its contraction, that means this inverse image, is also a prime ideal of A. And this fact also we have seen in the correspondence theorem. But that's not the case with extensions, always. If I is prime, I is an ideal of A, if that is a prime ideal of A, the extension of I need not be a prime ideal of B. To see why, you again consider that example, the example of embedding the ring of integers into the field of rational numbers. Say you take a non-zero ideal in the ring of integers. All ideals are principal ideals, many non-zero ideals are there. So you take one of them. Then you can see that the extension of that ideal is the entire field of rational numbers, and as such, it cannot be a prime ideal of Q, because a prime ideal by definition is the proper ideal, it cannot be the entire ring. However, how is this extension equal to Q? The non-zeroness of this ideal ensures that this is the case, this be the case. How? Well, you see, because I is non-zero, its image under F Well, in this case that will be I itself, because this is the inclusion map. So that contains a non-zero element also. And what is this IE? IE is the ideal of Q generated by that F image. So in particular it contains the F image within itself as a subset. So that non-zero element is in IE also. That means IE is a non-zero ideal of Q. But we know that Q being a field has only two ideals, the zero ideal and itself. So IE is not the zero ideal, so that way this is equal to Q. So we are seeing that contractions are much more well behaved than extensions. To better understand what's going on, we can factorize the function f, the homomorphism f, like that. Let us see what we mean by factorizing the function f. Instead of straight away having a function f from a into b, which is a homomorphism, ring homomorphism, we can reach b from a in two steps. First we go from a to f of a, and then we go from f of a to b via two other functions, p and j, where p is surjective, p is onto and j is injective, that means j is 1, 1. And the functions are actually these. P of x is nothing but f of x. So you take any element x from the ring A, and its P image is just its F image. So the function P is in fact obtained from the original homomorphism F by changing the second ring from B to F of A. That's it. We do not change the rule for the function, that is P. It turns out, and it's very easy to see, that this P is also a ring homomorphism and it is onto. And this onto-ness makes this P somewhat easy. P somewhat easy means the relationship between the ideals of this intermediate ring and the ideals of A, that relationship is given by the correspondence theorem because of this onto-ness of P. But we cannot simply just sit here, we have to reach B. So that we next do with the help of the mapping J. And this J takes any element y of f of A and gives that y back. Because do not forget that this f of A, what is f of A actually? F of A is the image of A under F. And the original function f was from A to B. So this f of A is a subset of B. And this J is just like this embedded. Here also Z is a subset of Q, f of A is a subset of B. So it takes an element of that subset and gives you that back. It does nothing else, it does not really change the element. And this is also a homomorphism and it is injective. In what sense is F being factorized in this sense? It's pretty easy, it's a straightforward thing to verify that the composition, J composition P is equal to F. So with respect to the composition operation, F has been factorized. When you have a large integer, then you factorize it and you see what its composition is in terms of prime numbers. So that way you can better understand the integer. Here also the situation is similar. Instead of dealing with f itself entirely, we think of j and p separately. Okay, so this factorization helps. But next, what is it about this entire thing, and how are these things related to ideals, extensions, contractions of these ideals? Let's see that next. So this is what the book says. For P, the situation is simple, much more simple. There is a one-to-one correspondence between the ideals of f of A and the ideals of A containing the kernel of F, which is something, okay, it will depend on F. And this is in fact what we have in the correspondence theorem. And in this correspondence, prime ideals correspond to prime ideals. But the general situation for that other homomorphism J is very complicated. Actually, do you see what is going on? Why are we suddenly talking about relationship or correspondence between ideals of this ring and ideals of that ring? That is because when you take an ideal of A and you find its extension, that extension is an ideal in B. So you are linking an ideal of A with an ideal of B. And when you take an ideal of B, its contraction is an ideal of A. So that way also you are linking ideals of different rings. So that's why that linkage can be understood in terms of something which is already available to us. But that thing comes only in one part of this factorization. That thing helps us understanding P. How P relates ideals of this ring to ideals of that ring. But how J relates ideals of this ring to ideals of that ring, that is complicated. And an example will illustrate why that is complicated. That, however, we won't see today. That example is a classic example from algebraic number theory that we will see next week. So let me just end this video here itself, and next week we will start with that example. So see you next week with that. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice day.